We're going to work problem 8.35 now. We're given box diagram configurations, and we're asked to write what element and group number this actually corresponds to. It's a two-part problem, A and B. We'll get into this here a little bit, discuss it, and talk about some limitations in the way that this particular problem is written. It's maybe not as simple as it seems. I'll show you why, okay? But let's just kind of dive in here and have some fun with it. So the first one, 4S and then 4P1. So 4S and then 4P1. So how in the world can we assess what is going on here? So I'm going to try to prop up my textbook here and explain it to you a little bit as best as I can. These periods, which are listed on the left-hand side of your periodic table, 1, 2, 3, 4, and so on, that tells you essentially the principal quantum number that you're dealing with, okay? So, and then the groups, so this is the S block elements. It has, S can hold 2 electrons, so you have 4s1, 4s2, and then these lighter blue colored elements are your 3D as you proceed across, and there's 10 of those. And then over here, you're in your P block. Okay? Those are your P block elements. That's where the P orbitals are filling. So if I've got my 4s2, and then I've got, 4p1, I can slide all the way over here. And it looks like I'm at element number 31, gallium. And that would be what my answer could be. This electron configuration is consistent with gallium, element number 31. But let me ask you one more thing. Element number 32, right to the left, is germanium. What about an ion of Ge plus 1? Let's say that I made that ion Ge plus 1. Just for saying sake, hypothetically. Would that ion have the same diagram? I'd argue that it would. Okay, now alternatively, I guess I could use zinc as an example. Now zinc is element number 30 on the periodic table. Okay, what if I made zinc minus 1 ion? Now these might chemically be kind of unrealistic and not common, okay? But I'm just being hypothetical here. What if I added an electron to zinc? What would its electron configuration be? Would it be the same as this? Right? I think it would. Okay, so while your book, I think, probably wants you to give this answer. Understand that when we start talking about ions, when we're adding electrons to atoms, or we're stealing electrons from atoms, we can start either filling in these holes or creating things which are isoelectronic with other things. All right, and that's an important concept too. So while this problem may have kind of seemed very straightforward at the start, you could argue it's a little bit more complicated than maybe what you thought at first glance. But anyway, let's move on. So the next one, we've got full 2s orbitals and 2p. Again, these only show our valence level. Okay. So back to the periodic table for a second. Here is period 2, starting with the lithium on the left. I don't know if you can read this or not. You probably can't, okay? But you can always look up the periodic table. So period 2 is lithium on the far left. This would be my 2s2, lithium and beryllium. And as I go across, boron, carbon, nitrogen, and so on, I fill up my 2p6. And then I get to what? Element 10, which is neon. neat, right? So this is fully consistent with neon's electron configuration, neutral neon. It's a noble gas, it's got the full S and P shell in its valence level. But, let's see, what about F minus 1, like a fluoride ion? What about my fluoride ion? Could I argue that this electron configuration is also wholly consistent with the fluoride ion? I think that I can argue that, matter of fact. Fluoride is one box to the left of neon. It's only got 9 electrons if it's neutral. But if it's F minus, fluoride, it's got an extra electron. That extra electron goes right here. Right? So this is also consistent with fluoride. To be honest, it actually can also be consistent with sodium plus 1. If you look where sodium at, it's element number 11. It's got one more electron, one more proton in its neutral form than does neon. Neon's only got 10 of each, right? But the thing is, if I make sodium plus 1, I've lost 1 of the electrons. So instead of having 11, I've only got 10. So anything with 10 electrons basically would look the same. That could be F minus, fluoride. It could be sodium plus 1. It could be magnesium 2 plus. That's another possibility that's going to have the same electron configuration. Or maybe it's aluminum 3 plus. That's going to have the same electron configuration. It's just aluminum atom that's lost 3 electrons. It'd be isoelectronic with neon. Maybe oxygen 2 minus. Oxygen 2 minus, oxygen's element 8. If you add 2 extra electrons, you've got 10. Same electron configuration as neon. Maybe nitrogen 3 minus. Okay, so my point here is that many different things can end up with this electron configuration. This is a neutral atom that's got this electron configuration. But all of these ions are isoelectronic with neon. That all of those ions have the same electron configuration as this, if you were to draw it out. Okay, so the wording of this problem, when I first read it, worried me a little bit, because you could make an argument that all of these are correct, and then answer that, and you wouldn't be wrong necessarily, okay? I think they probably want you to choose the one that's neutral, okay? But the learning goal for me considering this is that you recognize that when you form ions, the ions tend to form to be isoelectronic or have the same electron configuration as the nearest noble gas. Right? And that's sort of an important learning goal that gives stability to that ion. And that's why they react in the way they do.